All right, 4.1, the natural exponential function. What is the natural exponential function? Let's define it. So the function f of x equals e to the x. Remember we just learned about e. That's about 2.71. It's the end behavior of 1 plus 1 over n to the n. I guess you could use an x here if you really wanted to. The end behavior on the right side, the large side, or the positive side. But e to the x is going to be called the natural exponential. So this is called the natural exponential function. Why is it the natural exponential function? It works out really well in calculus, it turns out. And if you had any exponential function, you probably want e to the x here. Actually, it also turns out when we talk about functions, about exponential functions in general, like b to the x, I could always really change this base. Maybe I would have some extra stuff up in the exponent, but I could always change it to an e with some stuff up here and then another x. So I could actually do that with any number, it turns out. You can just change the base. But you got to add in some stuff in here. What's the nicest base to work with when it comes to exponential functions? Turns out it's e. So let's let's just graph some exponential graphs. So the first one will be y equals 2 to the x. So remember the base is 2 here. It's larger than 1, so we're going to get this picture. And we're going to cross at 1. If I plug in 1, I should get about 2. Maybe I should make that a little steeper. And that's y equals 2 to the x. Then if I plug in y equals 3 to the x, well, if I plug in positive numbers into x here for both of these, well, 3 to the x is definitely going to be larger than 2 to the x. I'm going to get something like this. And I guess this should be even steeper because it should cross over at 3 and 1. And still go through 1 on the y-axis when x equals 0. But when I plug in negative numbers, now I get a larger denominator in this one than in this one. So what's going to happen is the 3 to the x one is going to be smaller. It's still going to be positive. It's going to be below this graph. And let me make this one green now, I guess. Then finally, y equals e to the x. Well, remember, e is approximately 2.72. So it's between 2 and 3 is the important value. Like how pi is a little bit bigger than 3. It's really what's important. In a lot of the times, not always, I guess. But if you're trying to figure out the size of it, I mean, this is about how big it is. So there's approximately 2.72 to the x. So that's larger than 2, which means the graph on the positive x side should be larger than 2 to the x. But it's smaller than 3, so it should be smaller than the graph of 3 to the x. So in between here. And same deal on the other side. It's still between 2 and 3, so its graph is going to be between 2 and 3s. So that's basically e to the x. E is right about here, past 2.5. So let's call it e right there. So what can we use e for in some applications specifically? Um, Rather than arbitrary banking applications, which we already used E for, let's do more general applications. So the exponential, I guess this is a definition. The exponential growth and decay formula is so this is more of a function this time. We're only gonna want to have one variable be the thing that changes. Everything else are fixed constants. That's why I'm calling it a of t. T is going to be for time. And this is a sub 0. So a sub 0 is just the amount and the amount at time 0, so the initial amount or principal. But we're not talking about money in general this time. We're talking about anything that could grow or decay exponentially. But remember I said it doesn't really matter what base we use. And we can always change the base of an exponential formula. So let's use E because math people like it. And this is going to be the KT. K is going to be like our rate. It'll be a kind of rate. And T is again for time. I guess I'll write all that out. So this is where A naught is the initial amount. You might call it A sub 0. A naught is another way to say A sub 0. K is the relative growth or decay factor. This time it's going to be per amount of time here, but it's going to possibly be positive or possibly be negative. It's also going to be a percentage, but if it's positive, it's going to be a growth factor. If it's negative, it's going to be a decay factor. So it'll be called relative growth. That's when k is bigger than 0. And decay when k is less than 0. So it's getting bigger when k is positive, smaller when k is negative. T is the time. So let's do some examples. If the annual growth rate of the world's population is 1.6%, and in 2000, the year 2000, the population was 6.08 billion. What will the population be in 2030? All right. So we're going to use this specific formula. The growth rate here, this annual growth rate, is based on the continuous growth and decay formula. I guess I'm just calling this the exponential growth and decay formula. Sometimes you do call it the continuous version also. So if you hear continuous, that's what I mean. But specifically for us, we're only going to use this one specific formula. So you're never going to have to figure out the base here. It's always going to be E. There is an extra number here times E. You're going to have to figure that out, and you're going to have to figure this number out and this number out too, I guess. So we're using A of t equals, not P this time, but A naught e to the kt. So let's figure out what these things need to be. So what will the population be in 2030? That's the amount. And remember, this is the amount after some time. In this case, we're talking about amount of people. So this is the question. And this is when t equals a certain number. I don't just want the formula here. What is t going to be? Well, we might say that t is the year 2030, and that would be fine, I guess. But actually, usually you might have a starting point that's also another specific year. So rather than t be that actual year, let's just let it be years since 2000. So how many years? So 2000 will be the year 0. And how many years after that do we get to 2030? 30 years. So A naught is the initial amount. In 2000, we decided was when time started. So the initial amount was when time starts, and that's 6.808 billion. And let's just call it 6.08. I don't need to write out all those zeros. This is in billions. K is the growth or decay rate. Now, here you're going to have to see a word that says growth rate and then 1.6%. So the word growth is telling you to use a positive number, and 1.6%, we're going to turn that into a decimal version of percents. So it's positive 0. What was it, 1.6, 0.016. And then t, again, we figured that out before, it was 30 years. And I wanted to know technically what A of 30 is then in this case. Well, let's say looking for A of 30. That's really the question. So A of 30. That is equal to 6.08 billion times e to the 0.016 times 30. And with the magic of calculators, we get about 9.83, still in billions. All right, let's do one with a decay. So this stuff, radon 222 decays at a rate. And I guess if I say it decays at a rate, I should be clear. So let's say at an exponential rate. Or continuous rate of 17.3% per day. So this is the first time I'm using time that's not in years. Time's going to be in years for all those banking questions. But for arbitrary questions about exponential growth and decay, be careful. Time could be in any kind of unit. So this time it's per day. So I'll just say t per day. How much will be left after 3 days if you start with 100 milligrams. All right. A of T, A naught, K, T. Well, time was 3 days. So really A of 3 is what we're looking for over here. And A of 3 was the question. I want to know the amount that's left after 3 days. I'm starting with 100 milligrams. That's A naught. And then K, the exponential decay rate is 17.3%. So I'm going to move that decimal over and get 0.173. However, it is a decay rate. That means use a minus. So it'll be negative 0.173. And negative is for decay. So the answer is A of 3 is 100 e to the negative 0.173 times 3, 3 days. And what are we left with? 59.51-ish milligrams. All right, that's the end of this subsection.